Welcome back everyone. So today we start with mathematical modeling of systems. Remember what we were dealing with? In the last few lectures we had found out a way by which we can define a system mathematically, that is using transfer functions. Today what we will do is we will take two examples and we will try to find out transfer functions for those systems. These two examples will be very important for us because as we go along the course I will be using this example often. So let us get started. The first example that I will deal with is the mathematical model of a quadrotor. So what is a quadrotor? We had already seen what a quadrotor is. Basically a quadrotor is a device with 4 rotors in it. The rotors rotate, resulting in a thrust and torque, as a result of which the quadrotor moves. So today we will be dealing with only those quadrotors which moves only in the z direction. So we are putting an assumption on our quadrotor. We are basically simplifying the system. The reason for that is, if we simplify the system, it will be easier for us to understand the concepts, and as we go along in this course I will keep on relaxing these assumptions. So the assumption that we have in this case is that the quadrotor moves only in z direction. So here is a quadrotor which is hovering at a particular altitude. Now what happens in a quadrotor is all the 4 rotors in this case are rotating at exactly the same speed, and as a result of that they are creating a thrust. So since we have put the assumption that it cannot move in the other directions, so we are only concentrating on the altitude change of the quadrotor, and for altitude change, for the quadrotor to move along the z direction, we call this the z direction, which is the direction, altitude direction, we call that the z direction. So for the quadrotor to move along the z direction, the speed of the motor should equally increase or equally decrease for it to go up or down, as can be seen in this video. You can see that the quadrotor is moving up now, so the speed of the rotors were more. When the quadrotor is moving down, the speed of the rotors have been decreased, and at the end you will see that when all the propellers have come to a halt, the quadrotor comes to the floor. So this is how a quadrotor moves along the z direction. So in some sense you can actually consider that all the 4 propellers here or all the 4 rotors here are just only one rotor, because we are just moving along the z direction. So let us try to model this system. Model means try to find out the transfer function of this system. So for that we will define certain variables. The first variable being the thrust, which is being generated due to the rotation of the quadrotor propellers. So capital T is that, and here the independent variable is time, because over time the thrust will change, because if we change the speed of the rotors then the thrust will also change, and hence we are saying that the thrust variable here is dependent on time. M is the mass of the quadrotor, G is the acceleration due to gravity. So in that case, the first question that you should ask yourself when you need to find out transfer function of a system is, what is the input and output that we are talking about? Because if you remember, what is transfer function? Transfer function Gs was defined as the ratio of the output by the input in Laplace variable. This is what transfer function was. So in order to find out transfer function of a system, you should first know what is the input, what is the output. Unless you declare that, you do not even know for what variables are you finding out the ratio of. So in this case, let us say that thrust variable is the input. Why? Because when I change thrust, the motor changes its or the quadrotor changes its position along the z direction. So, I consider that thrust is the input. So, if I change thrust, the position of the quadrotor along the z direction changes. What is the output? Output is position along the z direction, and we call that zt. So, how much it has changed, that is being denoted by zt. So, then what is the differential equation that is governing this system? And it is simple physics. If you find out the free body diagram of this, you can easily find that out. You see, the differential equation can be written by the force equations here, which is thrust minus mg, which must be equal to ma. Mg is the weight, so you have to counter the weight first, and then whatever thrust is left, that will result in an acceleration along the z direction. Okay. So, you see ma will become equal to T minus mg. From here, you see a is acceleration, right, and we are accelerating along the z direction. So, therefore, a is nothing but double derivative of the displacement along the z direction, and hence a has been replaced by z double dot t here. So, we are left with z double dot t equal to t by m minus g. So, this is the differential equation. You can call this to be the differential equation or this the differential equation, they are the same differential equation. So, from here we go ahead. Remember one thing, what are we trying to find? We are trying to find out the transfer function of the system, and in this case y is nothing but zs and u that we have chosen is ts. That is the Laplace transform of the thrust vector, zs is the Laplace transform of the position vector along the z direction. So, z double dot is equal to t by m minus g. Now, notice one thing, that if I give t equal to 0, that is if I give 0 input to the system, what is the output of the system? The output of the system is output or the double derivative of the output of the system is z double dot t equal to minus g, which means if I go ahead and find out zt, I have to do a double integration and I will get some kind of a polynomial in t, quadratic form, which means zt is not 0. So, you are giving 0 input to the system, the output is not 0. Remember, in the last class we have seen this type of examples, and we know that directly you can say that this is not a linear system. So, there is a problem. We are dealing with linear system in this course, right? Whatever transfer functions, whenever I have talked about transfer functions, we said that those differential equations that we got are of LTI system. Linear system is very important. Time invariance is fine, because we can always assume it is time invariant, because today whatever you do, tomorrow also the same thing can be done on the quadrotor. So, we can assume time invariance. Causality is also implied, but from these equations we can see that the system is not linear. What should we do? Well, it turns out that it is not a big problem in this case, because instead of taking thrust as the input, we can take something else as the input as well. So, what if we consider acceleration as the input? Although it does not look like why should I take acceleration as an input, but you see these are the trickeries, I should not say trickery, but these are the ways by which you can convert your differential equations into linear equations also in some cases, not always of course, in some cases, and this is one of that case. You see, if I take acceleration as an input, now what happens? You see, acceleration and thrust has a direct relation between them. M here is a constant, g here is a constant. So, if I know A, I know T as well. So, why don't I analyze the system taking acceleration as the input? And as soon as I take acceleration as the input, you see our life becomes easier, because what is acceleration? Acceleration is double derivative of the position vector here, right? So, z double dot t equal to at. I can say position vector, do not get confused by the word vector. Vector or variable is the same here, because here we are just dealing with one variable. So, it is a 1 cross 1 vector kind of a thing. Okay. So, do not get confused because I am using the word vector, it is a habit basically. So, that is why I am using the word vector. So, now you see z double dot equal to A. Well, this is the differential equation. Remember, now we are considering that our input in the course, I will write input sometimes in this form I slash P, it is just a short easier way, quicker way of writing. So, input in this case is acceleration and output in this case is the displacement along the z direction. So, now if I go for Laplace transform of this differential equation, because remember I want to find out Gs, now the new Gs that I am trying to find out is As by Zs, where Zs is the Zs by output by input, right, not input by output. So, output by input, As is the Laplace transform of At and Zs is the Laplace transform of Zt. So, from here directly we see that Zs by As comes out to be 1 by s square. So, this is the differential equation, this is the transfer function of the system considering acceleration as an input. We are no longer taking thrust as an input, but that is not a problem for us because we know the relation between thrust and acceleration, there is a direct relationship between them. So, it should not be a problem for us. And when I make it into a linear system, our life will become easier because whatever we are going to learn in this course is for linear time invariant systems. So, those whatever theory we learn in this course I can directly apply now for this considering acceleration as an input, and then whatever results we get we just convert it back to thrust, that is it. So, this is the mathematical model of a quadrotor. Again remember, we have not gone into the full fledged quadrotor model. This is a quadrotor which has a constraint. The constraint is that it can only move along the z direction. Okay. We will come to the other cases where it can move along 2D plane, along in the 3D plane, all this as we move forward in this course. Great. So, one case we have handled, one system we have handled. Now, notice one thing, when the quadrotor moves, what is it that is making it move? The propellers, right? The propellers are rotating, as a result of that you are getting the thrust, you convert it to acceleration and then you know where to go, because you have the transfer function, you know how the system will behave. But when the propeller is rotating, it is basically a motor, right? It is a simple motor that is rotating. If you just strip down the quadrotor, you just take out one of the motors. So, basically what we are doing is, you have a motor, you are giving some voltage input to the motor, and based on the input that you are giving to the motor's rotor speed, the shaft speed is changing. This is just one of the examples where motors are so important. You take a robotic arm, in a robotic arm also when the joints are moving, the joints have motors in it. How fast will the joints move? To what angle should the joints move? All this depends upon your motor. So, motor is a very, very important component in any robotic system that you take. So, it is better that we understand how to model a motor then. So, the next system, that is why we will be dealing with the next system, which is a DC motor. Okay? And again, motors can be of different types. Okay? It is not possible to go into all types of motors and find their mathematical models in this course. That you can do on your own once you learn how to do it. Instead of that, I am concentrating on armature controlled DC motor. If you are not familiar with DC motors, I would urge you all to take up any machines book and go through how does a DC motor work. What is the meaning of an armature controlled DC motor? In nutshell, it is basically you have an armature, you give voltage input to that armature, rotates in the presence of a magnetic field. The magnetic field maybe field is generally, you have these fixed magnets which results in that magnetic field, and that results in movement of the motor shaft. So, please go through the basic principle of motor. Remember one thing, when you do mathematical modeling, it is very important that you understand the basic principle of the system, otherwise you won't be able to write down the differential equations. Okay. So, here we will be dealing with armature control DC motor. So, in an armature control DC motor, the first question that we should ask, again we are trying to find out transfer function, remember. So, what is the input, what is the output? Again in this case, since I have already motivated with the example of a quadrotor, so why do not we take the input to be the voltage that is given across the terminals of a motor. So, here you have a motor, you will have terminals here. So, in these terminals you will give some voltage, based on what voltage you give, the motor shaft will rotate. Okay. So, at what speed is the motor shaft rotating, that is the rotor speed or the angular velocity of the shaft, motor shaft, that is our output. So, what voltage should you give, and corresponding to that what will be the angular speed of the shaft, that is what we are trying to see. So, the output is angular speed or the rotor speed of the motor, and the input is the voltage that you give or the armature voltage of the motor. Okay. So, let us go ahead. So, when you have an armature winding, the armature windings can generally be modeled as an RL circuit. Okay. So, because there are windings, so it will have inductance, it will have resistance as well. So, this is the basic diagram of an armature winding, maybe the circuit diagram of an armature winding in some sense. So, you have a resistor with Ra is the resistance of the armature, La is the inductance, then Ia is the armature current or the current flowing through this because of this armature voltage. So, this is your input to the system, remember this is your input to the system. Okay. We are giving this as input to the system. As a result of this motor shaft, this shaft is rotating by some angle, now that we are denoting by theta. Okay. And there is a torque generated because of that, and that we are denoting by Tm, motor torque. Okay. Remember these are all time dependent variables, although I have skipped the time variable here, these are time dependent variables here. Okay. These are time dependent variables, Ra and La are only constant variables here. Okay. So, now if I see what is the torque that is developed in this motor, that is directly proportional to the current that flows through this circuit. Okay. So, Tm is directly proportional to the armature current, and so of course, there is a proportionality constant involved, that proportionality constant is called motor torque constant. Okay. So, Tm equal to Kta. Remember what we are trying to do now, we will try to find out the ratio of, what do we want to find out the ratio of? The output was, I have already written it out. So, the output was shaft speed or rotor speed. So, let me call it omega s, okay, angular speed, omega t is the time domain, omega s the Laplace domain, and the armature voltage is EAS, the Laplace transform of this variable EAT. Okay. So, we want to find out the ratio of omega s by EAS. So, for that we need to find out the differential equation. So, the first equation that we get is Tm equal to Kta. Then because the armature is rotating in a magnetic field, so you will have back EMF. So, Eb is the back EMF, it will oppose the input voltage that you have. So, here the polarity therefore is plus and minus here, and the back EMF will depend upon the speed at which the shaft is rotating. So, Eb is proportional to d theta dt, which is Eb is equal to Kb d theta dt, Kb being the proportionality constant here called back EMF constant. These are parameters of a motor, you will find these parameters generally in the spec sheets. Now, if that is the case, you see EAT, so what is the circuit looking like now? So, circuit looks something like this. You have an input EAT, armature voltage, and then here you have a back EMF which is opposing the input voltage. So, this is the circuit looking like, and you see the current direction was in the other direction. So, you have this. So, from this circuit you can get using simple KVL rule, you can directly find out this. So, we have this equation. So, we have 3 equations 1, 2, 3. So, 3 equations we got, and then there is another equation. Let me just rub this. Okay. So, there is another equation which will come, because when you connect a load to the shaft, the load will have its own moment of inertia and there will be some viscosity there. So, that will result in the torque equation. The torque here is TMT, remember. The torque equation will therefore be Tm equal to J d2 theta by dt2 plus B d theta dt, where J and B are the moment of inertia and viscous friction coefficients. Again, these are like basic equations in mechanical systems. So, you might have to go through these on your own, but these are like physics, basic physics equations. Okay. So, the torque equation is Tm equal to this. Of course, you can also have a spring constant here. In this case, I mean, I do not think there will be spring constants, but I mean, it depends upon the load you are using. So, for now we are just neglecting that. Even if you keep it, it is fine. Anyways, so now these are the 4 equations that we get. So, we have 4 equations. Again, we are trying to find out Gs. What was Gs? Gs was omega s by E as. This is our objective, which means I have to eliminate all variables and write down this equation only in terms of omega and Ea. So, the first thing that we will do is, instead of working in the time domain, we will convert all these equations to the Laplace domain, which we can directly do. Remember, when we are doing this, we are considering initial conditions to be 0, because to find out transfer function, initial conditions must be 0. So, we have considered all initial conditions to be 0. These are the equations that we get. So, now let us try to work out these equations and try to find out omega by EAS. Okay. So, here see from the first equation, EAS is equal to SLA plus RA whole into IAS plus EB. EB can be written as SKB theta S. Okay. And so, this comes from putting C in A. Again, here you can see from B in D we have TMS equal to S square J plus JB theta S. So, theta S, this is equal to KT IAS. Okay. So, I can multiply. So, now KT multiplied by, let me call this equation number E, KT multiplied by equation number E gives us KTEA S SLA plus RA KTIA, but then see KTIA I can replace from here directly. So, I will just replace it directly here, so that I do not have to write it again. Theta S plus SKB KTS, KT was multiplied both sides. Now, from here notice I can rewrite this again as KT EAS SLA plus RA. Here see I can take an S out from here. So, SJ plus B plus, so KB KT whole into S theta S. So, now KT EAS equal to SLA plus RA SJ plus B plus KB KT. Now, notice we want omega, right, omega S, but what is omega? Omega T is nothing but d theta dt, right, and if you take Laplace, this is what you get. This is the equation that you get. So, I use that. So, that means this becomes omega S. So, which means omega S by EAS comes out to be KT by SLA plus RA SJ plus B plus KB KT. So, this is the transfer function that you were looking for. Okay. Now, in this example I took output as speed of the shaft. You can also have output as angular displacement of the shaft. In that case, we would have found out theta s by EAS, but since we have already found out omega s by EAS, you know omega s is nothing but s theta s. So, this is nothing but kT by, there will be an s term coming here, s LA plus RA Sj plus B plus Kb Kt. Okay. So, if I take theta s by EAS, this will be the transfer function. If I take speed, angular speed by EAS, this will be the transfer function. These two transfer functions will be very, very important for us as we move ahead in this course. I will keep on recollecting these transfer functions, okay, especially the structure of the transfer functions, because see LA, RA, JB, all these kind of different values, right. But important thing is, notice that in this case, in omega s by EAS, the denominator is second order, whereas in theta s by EAS, the denominator is third order. Okay. So, that will be very important for us, and I will keep on recollecting this transfer functions as and when required. So, I will stop today's lecture here, but as we move forward in the next lecture, what we will try to see is that how do we find out transfer function of a system if we do not even know the differential equations. So, basic idea is, can we find out transfer function of a system experimentally? Is it possible? That is what we are going to look into as we move forward in the next few lectures. Okay. I will stop here today. Thank you.